All right, so we're going to start with a short quiz. So you can use your formula sheets, but nothing else, and no working together. All right, so take out a sheet of paper, put your name on it, put the date. Just put your name and the date. Today is the 25th. Okay, so very important. I want to know what you can do. I don't want to know what your neighbor can do. So even though y'all are sitting like this, I expect you to treat this like a test and do your own work. All right? All right, so here's what I want you to do. For number one, I want you to imagine that you had an integral that had this expression in it. I would like to know what your trig sub would be. So what would your trig sub be? I would like to know what the square root of 16 minus x squared would become. And I want to know what dx is. So there's kind of three parts to this. Understand? What's the trig sub you would do? What does this turn into after you do the trig sub? And then what does the dx in the integral become? Does that make sense? Are you sure? No? What's that? Okay. Last class we talked about integrals where you'd see this sort of expression in it. You make a certain trig sub. And when you make that trig sub, then that square root thing turns into something very nice. I'd like to know what it would be in this case. Like what would that turn into with that trig sub? And then finally, what would the dx become in the integral? Okay?
So just
the
dx of square root of 16 minus x squared?
No, the dx of your trig sub. Because your trig sub is going to be, you're going to let x be equal to something. Okay, that's what I want to know. And then whatever that is, I want to know what dx is, which is the derivative of that. Okay? That's number one. Number two is what would you do if it were backwards? And number three is what would you do if they were summed together? All right, so same three questions. A, what's your trig sub? What does the root turn into? What's the trig sub? What does the root turn into? There. Okay. What? We're not doing any integrals at all. We're not doing any integrals at all. I'm not asking you to integrate anything. I'm asking you if this were to appear in an integral, what would your trig sub be? What would that thing turn into? And what would dx be? That's it. You're not doing any other work. Because this is the first step of doing trig sub. You have to be able to establish these three things before you can move on in the problem. That's all I want to know is like, where are y'all right now in terms of knowing what the trig substitution is and what those expressions become. If you don't know, you don't know. I just want to see where y'all are with this.
So A is to find the trig sub and B is...
Then if you use that trig sub, then what does that turn into?
I see.
What's the derivative of your trig sub? started a little quiz here. We're going to go 5 more minutes. So I need to explain this to you. All I'm asking is, if we're doing an integral where we see something like that in the integral, then what would your trigonometric substitution be for that? And then if you make that trig sub, what does that thing then turn into? Because it gets nice. And then what's the derivative of your trig sub? Okay, and for those 3. Okay. Yes.
So we're taking the derivative as it's written under the radical, like right here, just that. We're talking about just that.
Just in part A.
Thank you.
All set. Yeah, if you have it, you can turn it in. I'm giving you like 1 more minute. Thank you. Oh. Okay, thank you, thank you, thank you. Thank you. Thank you. Okay, thanks. Okay, thank you. Okay, thanks. Okay, about 15 seconds.
I have no idea.
Okay,
I just wasn't here.
okay. Okay, that's time. Last call, last call. Thank you. All right, so this, I'm not sure how this will be calculated, if I'm going to actually take it as a quiz or not. Let me see how everyone did. Anyone else?
Maybe just the completion rate?
Completion, I don't know about that. So look, Last class, I realized we talked about trig sub. We just got into it, did a few problems, and then, but we also, I told you we're going to spend more time on it today. And my idea behind this quiz was, you know what, am I recording? Let's see that. Yes, okay. The idea behind this quiz is that, you can't do trig sub if you can't get it set up to start. Like, if you don't know what you're supposed to do with it, then it's, how are you going to do the problems, right? So this quiz was like, let's see where everyone is. And I thought, well, you know what, this is a lot of information to remember. But you're allowed to have your formulas. I told you you could have your formulas, right? So if you go to our website, Canvas, in the folder that says Formula Sheets, there's a thing right here that if you click on it, trigonometric substitutions and trig sub right there. Like, you should have this in your hands right now. You should be using this on this quiz right now if you don't know what to do, because this tells you, if you see this expression, what the substitution is going to be. If you see the expression, what the substitution is going to be. Okay? All right. So
We can have that
you can have that. Yeah.
on the test?
Yeah, I told you day one, anything in that folder that says formula sheets you can have on a test.
My God.
Yeah. So this right here should have made this quiz pretty easy. So like if we go back and we look at, let me see, should I keep this up here, or? I'll keep it up here because we can use it to answer the quiz, I guess. The first one I talked about or asked you was the square root of 16 minus x squared, right? So I said, what's the trig sub that you're going to make for that? Well, if this is the expression you have, then you're going to make x be what? In this case, 4 sine theta. Okay. What will the square root of all that stuff turn out to be? Now that is not here. That is not in here. All right? The way you can figure out what this will turn out to be is just replace x with this. Okay? So if you do that, you get 16 minus, square that, you get 16 sine squared. We did this in class last time. Factor out a 16, pull out the 4, 1 minus sine squared becomes cosine squared, and then you take the square root. So at the end of the day, you get 4 cosine theta. And then that's the answer to part B. And then the answer to part C is what's dx? Well, you just take derivative of this. And that's going to be 4 cosine theta, d theta. So those are the answers to that first one, right there, right there, right there. Okay, and then when you have it the other way around, x squared minus 16, use this bottom one. So you would have made the substitution for secant theta. And then you would have figured out what that root turns out to be, and then you would have taken derivative. And okay, so today, as I'm moving through the examples today, I am using this, all right? I'm going to be using this to do the problems. Clear? Okay.
Mistake I made, I forgot to square the x.
Oh, underneath the root?
I
Yeah.
saw that at the end and then ran out of time.
Okay. So I said we're doing more examples today, right? More examples. Oh, and last class, I stopped. We were doing a problem and I stopped and I said, we ran out of time. So we come back and pick that up. It was like sine to the... Yeah, and we had taken it all the way down to this trig stuff, right?
Yeah.
Okay, if you remember that problem, I changed the problem right at the beginning because it was originally x cubed, and there was a way we could do it with a u substitution. I didn't want to try and cheat and go around, not cheat, but I wanted us to go through some difficult stuff. But by changing it to an x to the fourth, we wound up with something that we can't do at the end. So that expression that we had at the end, I said we get back to, yeah, it's not happening. Okay? Which leads to like a bigger story here. If you were to take all functions, okay, all functions that exist and throw them into a big pot, and then just go in there and close your eyes and grab a function out, the chances that you can find the antiderivative of that function is essentially 0. Right? Like us human beings using our techniques that we're trying to learn, the probability that you can actually integrate a function, just random function, is pretty much, it's not happening. Which means that we have to have ways of doing antiderivatives numerically, like with a computer, with a machine. So there are numerical integration methods that when you go to Wolfram Alpha and you type in, a function, you say integrate, it's coming up with an antiderivative, and it's using power series and things like that we'll talk about later. So I guess it's kind of depressing because you go through all of this and then you realize in the real world, like, these techniques are not going to serve you well when the problem that you're getting comes from the physical situation and you don't get to doctor the problem up perfectly so it works. Does that make sense? Like, these problems in the book are very carefully chosen so that they work. So, all right. But you still need to know integration because in differential equations you have to be able to integrate. So the techniques are good. Just big picture is kind of sad. All right, so because of that, we're just going to stop that problem. We're just going to pick up with a new one. So here's the new problem for today. First one, get us going. We want to find the antiderivative here. So look, I was asked at the beginning of class if U substitution is something that we should just always be thinking, and that's absolutely yes. Like, you always want to be thinking U sub if you can start to chip away at it with U sub to start. If you look at this initially, you're like, okay, square root a squared minus x squared. This looks like trig sub, right? It looks like it's perfectly set up for trig sub, but we do want to consider the fact that maybe U sub would work, right? So in order to use U sub, we would have to see something in its derivative. So do y'all see something we could do? I mean, we can maybe do U is x squared, right? U is equal to x squared, or maybe even we could do U is 9 minus x squared. Maybe we can do the whole thing. And it's not going to work. Yeah, because the derivative of this would be 2x. So maybe what we could do is we could rewrite this with an x peeled off. Right, like that. And so if we do that, then let me see. Let's go with this one. The derivative of this would be, what, negative 2x dx? So we'd be off by a constant. Here's the problem, though. If I were to rewrite this, I know that the bottom would become what? If I'm using this one, the bottom would be root u, right? The x dx would become negative a half du. That's just taking this and solving for x dx, right? But what would the x become? We'd have to solve that for x, right? So now if we solve that for x, we're going to get like x squared equals, let me move things over, 9 minus 1, like that. 9 minus u. And then square root. So we're going to wind up getting like square root of 9 minus u. And that, I think at that point, we're kind of still jammed up. There's not much we can do with that. We can't split this into two things, right? Like we can't go like 9 over that, this over that. We could put it all under one root, but... Pardon?
If you did another substitution with 9 minus u, you'd have a radical of something.
So maybe we could do another substitution, right? So we could keep chipping away, but this is not working out as nice as we want it to. So let's just see if the trig sub does it. Because trig sub, even though it seems like kind of this big thing, like once you get decent at it, it's not that bad. Like you make the substitution, you got a trig integral, and you keep going. All right, so let's do our trig sub. And what is the trig sub here? X is going to be replaced with a sine theta. So 3 sine theta. We know automatically from that this is going to become what? And we could go through all the work with it, right? Replace the x, but 3 cosine theta every time. It's gonna, so if your trig sub is x is equal to a sine theta, then the square root part's always going to turn into a cosine theta. And then the dx part is going to be replaced with 3 cosine theta d theta. Just don't forget the d theta. That's the big difference between this one and this one. And now we can rewrite the integral. So this integral becomes, let's see, x squared. So 9 sine squared theta. That's the x squared on top. And then the root part on the bottom becomes 3 cosine theta. And do you see how the biggest mistake that I see students make is they forget the dx part? Like dx, students will just write, okay, d theta, and that's it. But no, you're replacing dx with something, and it actually has a lot of junk in it, doesn't it? So you've got to make sure that this piece right here becomes what it is, 3 cosine theta d theta, right? And now some pretty nice things happen, right? You've got some cosine theta cancels, 3 cancels. So we've got like, see, 9 can come out, sine squared theta d theta. And that, drum roll. Jace, you're up. How do we do that, Jace? Yes, how? How do you do the antiderivative of sine squared, Jace? Power reduce. Okay. So can I pull that 1/2 out? Is that okay? And then what is it?
Sine 2 theta.
Close. 1 minus, right? 1 minus sine, and then double the angle, right? 2 theta, d theta. Like that. Yeah, I don't know why I'm. Yes, thank you. I don't know why I'm. I was listening to Jace. That's why.
Yeah.
Yeah. Yeah.
Over here thinking about how
No, I mean you answered what at least you said power reduce. I mean that should be, when you see that now, it should be like the first thing comes to mind. So power reduce that, get the formula. The 1/2 came out, right? And then just integrate each of those term by term. So the antiderivative of 1 is just theta because we're in terms of theta. So theta, and then minus the antiderivative cosine of 2 theta is 1/2 sine 2 theta. And haven't we seen this before? Like, haven't we had one like this before? I think we have. Any questions up to that point? Chris, you're next. Oh, you're asking? Yeah, sure.
So I get confused with the power reducing and then the ones like directly we can solve their sine squared theta and 1 minus cosine squared theta. Like,
Okay, so like with the Pythagorean identity, you wouldn't want to use a Pythagorean identity here because if you turn that into 1 minus cosine squared theta, you still have squared. So the whole idea is to get rid of the squared. And so that's why we use the power reducing. And then you can integrate these each one term by term. And fortunately for us, we do know the antiderivative of that. All right. So Chris, this, you're okay up to this after the antiderivative? So we need to get theta back to x. So how are we going to figure out what theta is? What can we use for that? The triangle? Okay. We have, this is our main piece of information right here, right? Can you solve that for theta? Mm-hmm. Solve it for theta. Arc sine? Okay, not yet though. You have to do something before you do arc sine. Because you can't have that 3 there on the right. So, okay, so this is the same as x over 3 sine theta. And now do arc sine. So arc sine of x over 3 equals theta. Good? Okay, so I can replace this with arc sine of x over 3, or 1/3 x if you like that. But then I have to go somehow figure out what sine of 2 theta is. And my reference triangle that I'm going to draw from this is going to look like what? So help me label some sides. Let's see who's going to help me label. Chris? Where's Chris? That's Chris. So help me draw this triangle.
So sine is, would the x be on?
So I'll put theta here. How about that? Okay, so x should be,
Would it be on the opposite side?
opposite side, and then you're using this, right?
Yeah.
Okay, so that's opposite over hypotenuse. So here, right? And then from that we can get the third side by just doing some algebra. So that's going to be 9 minus x squared. And remember I said, hey, that thing, we've seen this before, right? That's that weird thing in there. Okay, so can we now use this, or do we have to do something first? We have to do something first, don't we? This is sine of 2 theta. We just know about theta. We don't know about 2 theta. So we have to use our pre-cal formula for that. We've done this before, the double angle. That becomes 2 sine theta cosine theta. And fortunately for us, that 2.5 cancel.
I have a question.
Yes.
So are we not using inverse sign?
We only use the inverse sign to get what theta was. Because I want to know what theta was, I don't need a triangle for that. I can just go algebraically and find theta.
Okay.
But to figure out what sine theta and cosine theta are here, to get this part, I need to go to a triangle. So when I look at this triangle, I know what sine theta is, and now I know what cosine theta is.
I see.
Right?
Okay, yeah.
Maybe I should have done this step first. That would have said, this would have told us, oh wait, we need a triangle. I just always draw the triangles. Yes?
And the reason we use that identity is because the 2 is inside the sign. That's why we turn.
That's right. Yeah, because it's kind of like, if I tell you that I have a triangle that has an angle of, let's say, 15 degrees, then sine of that, cosine, tangent has, they have certain values. But sine of double that angle, right, is something different. So we needed a formula. We know everything we need to know about theta, but in our answer, it's double that. So we use a formula to go back to theta, and then we use our triangle. All right, I'm going to keep going, yeah? Okay, so I'm about to use that triangle I just erased. But I think I can get it all here. So we should have 9/2. Okay, and then this part right here, theta became arc sine of x over 3. And then the 2.5 cancel, so minus. And then now we go to our triangle. Sine of theta, we already knew was x over 3, times cosine of theta, which was the root 9 minus x squared over 3. And then plus c. I mean, there's some stuff we could do. We could multiply 3 times 3 and get 9 and distribute the 9/2 through. But I think we're at a point where it's got everything's back in terms of x, right? If we take the derivative of that, if we take the derivative of this, what should we get? X squared over the square root of 9 minus x squared, the original integrand that we looked at. Any questions before I move on to the next example? Did you all finish that? Did you try it the other way and finish it, or no? No? Because remember in the beginning we did a U sub, and then you said we could, did you?
I didn't try it. It looked
You
like
didn't?
it was going to work.
Yeah, I think it may have, but yeah. I'm going to give you a problem here today that you have no choice but trig sub, all right? So, all right, how about this one? Square root of, let's change the variable up just because, I mean, we can. There's nothing that says we have to continue to use x's. Yes, uh-huh. Yeah.
I know, in very, very previous sections, we had, it was, x to the 5th over the square root of x to the 4th plus 1, and it was, stay tuned, because we didn't know how to do that yet.
Mm-hmm.
Would we be able to, can we do that with what we know now, or do we just have to wait a little bit longer?
Do you have it right in front of you? Let me just see, because
Because it looks like x squared plus a squared.
Yeah, we could probably do that with this now.
This is the state table.
Yeah, we could probably do that because you could look at that as x squared squared plus 1 and make a u substitution, and then you'd use trig. Maybe we'll look at that after. Yeah. I just have a lot on my like the problems I want to do today, so I don't know if there will be time for that one. Okay. All right. So you've had sufficient time to look at that now? I don't think a basic u sub is going to work here. Like if these were flipped over though, right? What if these were flipped? Then you would definitely go with basic u sub. Do y'all see that? Because if they were flipped, you could let the u be this, and the derivative of that is just going to be like y, right? Something with y, and you would have the y on top and everything would work out great. But that's not the way it is, and you can't just flip it over, right? So, trig sub, let's try that. So what is the substitution we're going to make, Martin? Martin.
That's going to be a secant.
A secant. You all agree? Okay, so what's a here? 7. So I'm going to use y, not x, right? Because my variable is y. It's going to be 7 secant theta. Okay, now, let's see. What will the square root of y squared minus 49 turn into? 7. That's the derivative of y. I'm saying this square root part. What is that ugly square root thing going to turn into? It should be 7 tangent theta. Where's that coming from? Replace that with 7 secant theta, right? Square it, so you get 49 secant squared theta. Take out a 49, take it out of the root, and what you're left in there with is secant squared minus 1, which is tangent squared. So, do I need to show that? I mean, do y'all want me to show that?
Yeah, no, I
You don't? Okay, so I'm not showing this step because it becomes too tedious to have to do it every single time. I'm replacing y with that, right? So when I square that, I get 49 secant squared theta, and then I had minus 49. Okay? So what we looked at this problem, we said, look, we're going to replace our y's with that. If we do that, then this square root of y squared minus 49 becomes this. And now I can take a 49 out of both, and the 49 out of the root, which is a 7. What would still be underneath that root? Secant squared theta minus 1. But that's a Pythagorean identity. That's tangent squared theta. And so this becomes the square root of tangent squared, which is just tangent. So you know how when we make a trig sub of x is a sine theta, that the root always becomes a cosine theta? When we make a trig sub of x, or in this case y, is equal to a secant theta, then the square root thing is always going to turn out to be what? A tangent theta. All right? Always. So that makes sense?
Thank you, sir.
Okay. So we also need to know what dy would be. Those are the 3 things we need to know. So what would the derivative of our substitution be? 7 secant theta tangent theta d theta. Yeah. So here are the things that I concluded. This right here, and that right there. Those are the 3 pieces. And now we can rewrite the whole integral. Luis.
It's gonna be 7 tan theta on top,
7 tan theta on top.
and then 7 secant theta on the bottom.
7 secant theta on the bottom. Everyone agree?
And then your dy,
Then dy, which is
7 secant theta,
secant theta tangent theta d theta. I'm running out of room. That's the new integral. I'll just get rid of that. Okay, so rewriting, taking my three things, plugging them in. And we get some good cancellation here. Secant's gone. 7's gone. Tangent squared. Yes?
7 tangent squared.
7 tangent squared. So we have 7 integral tangent squared theta. D theta. Michelle. Hi. We good up to this point?
Yeah.
Yes?
You should have called me when it was easy. I don't know. No.
So this one can be done like the hard, brutal way or the easy way.
I'll take the easy way.
Yeah, so let me just ask you this. If that was secant squared, would you be happy to see secant squared? Because, like, do you know the antiderivative of secant squared?
On my corner sheet.
No. In Cal 1, the derivative of what is secant squared? No. No. Derivative of, no. Derivative of tangent of,
Can you ever get sine square over cosine square and then put the half formula?
you could do sine squared over cosine squared, but the half thing I think would turn into a problem because you would have stuff on top and bottom, and so you couldn't integrate them term by term. It would be kind of messy.
Wouldn't it be
I think I heard over here also, yes.
secant squared minus 1, and then you can take.
Yeah, tangent squared, just the Pythagorean identity. Pythagorean identity. Tangent squared is the same as secant squared theta minus 1, right? So I could do 7 integral secant squared theta minus 1. That's tangent squared, right? So I haven't done anything other than use a formula. And Michelle, I was saying that because if you know what the antiderivative of secant squared is, then this becomes easy because you can take the antiderivative of that, that's just tangent, and then the antiderivative of 1 is just theta. So without that step, that problem's going to be a little bit tough. You could try all these different things, but the identity takes you right to it. I'm not quite sure how to teach that. You know, it's recognition of things. There's a lot of things that have to be recognized. You can't go backwards if you can't go forward. You know, that's when we talked about this in the very beginning of Cal 2. It's like the more comfortable you are with taking derivatives, the easier it's going to be to go backwards. All right. Are we good with that? Are we done?
No.
We're not done because we need to know what theta is and we need to know tan theta. So to get the theta part, how are we going to get the theta part? Just go up there and solve for theta on the equation. How are we going to get tan theta? Triangle. It turns out in this problem we can actually get tan theta because we have it right here. We can just divide both sides by 7 and we have it. But I'm drawing the triangle because, yeah, practice, exactly. So from here, you won't always have it. Like this won't always match, okay? So you have to have a triangle. So I first divide both sides by 7. And now I take inverse secant on both sides. Pardon?
How come you use secant instead of tangent?
Instead of tangent? For what? The inverse thing?
Oh, you're doing theta first, okay.
Yeah, I'm getting theta first.
My bad.
Yeah, so there's my theta. So I'll replace that with that. And then my triangle, I'm not going to call on you, Edward, because you weren't here last time. Gina, I just want you to draw me up the triangle here, or help me draw it. Here's your theta, right? So which side's which here?
7 is on the bottom, y is the
Y is the hypotenuse, 7's on the bottom. Y'all agree? Is that secant of theta is y over 7? Yes. Good. And then this side right here, y squared minus 49. There it is. Hey, there it is, peeking its little head out again, right? And now we know what tangent theta is, right? Tangent theta would be this side over this side, which is, again, what we would have got right here. Yes?
So could we have gone by when we had tangent squared theta and just done it then?
Done what?
Substituted at that step.
Substitute what? This?
Yeah. If you square it, you have y squared minus 49 over 49, and you can take an integral of that.
Let me see. No, because d theta has to change to something. Right? So you're saying I can replace this with stuff with y's in it, right? But then your d theta's got to go back to what its y's are. So your d theta would have, I've erased it, but your d theta would have to be replaced. And unfortunately, that would take you back. That would actually get you back here at some point. If you go try and get back to, in terms of y, you're going to wind up back here. Yeah. Okay, so tangents on, okay, we were ready for the answer here. It is 7, and then we have square root of y squared minus 49 over 7, and then minus the inverse secant of y over 7. And all that plus c. There it is.
Reasonably, could we
Distribute.
use,
You could get rid of this 7,
yeah.
but you can't get rid of that one. So you just have to put the 7 in front of that. Okay, so are you kind of catching on? Yes?
So if it's something different, I switched the secant to cosine.
You switched the secant to cosine? At what point? Before you did this, or like way back when?
Before I did that.
So you're using inverse cosine? It's fine.
Okay.
Yep. Yeah. Turns out no issues there. In fact, if you type this into like Wolfram Alpha or something like that, it might use inverse cosine. It just depends.
Okay, yeah.
Yeah.
This is 7 over y.
Yeah, exactly. It's flipped. There's a lot of problems. A couple of students have approached me about this, like especially with problems that involve trig stuff, where our answers may not look the same. And it's just because there's so many identities getting back and forth between, you can move from sine to cosine to tangent and stuff. So anytime I type something into a calculator, like a Wolfram Alpha or even like the TI-89, anything with like a computer algebra system, those answers are always so different than anything I would ever get by hand, because they use so many things in their algorithm to simplify that, you know, my answer is just never going to look like that. All right, here comes another one. Are y'all kind of catching on though to like how this works? Now this problem I pulled out of another textbook this morning. I have not worked it myself. I have no idea what's going to happen here, but I'm pretty excited about it. We're using R, big deal. So because I have not worked this problem out before, I am going to not assume that it's trig sub just right off the bat. Okay, I am going to consider some other methods first, but I hope it's trig sub. I don't see a basic U sub. That R to the 8th in the bottom really seems problematic.
is it reasonable to do?
Yeah, we could do R squared to the 4th, but then if we do that, yeah, when we do trig sub, maybe, I don't know.
Is it possible to maybe actually work out, like FOIL it out, and then put them all, each term over R?
What do you mean FOIL them out?
Like do the FOIL and then divide by 5, or how do you do the 5 over 2 power?
Yeah, yeah, what does that mean? What does 5 over 2 power mean? It's the square root to the 5th power. It's square root to the 5th power. But it's the square root, hold on. So that is the square root of 1 minus R squared to the 5th all over r to the 8th dr, right? So I'm actually starting to think trig sub, right? Because that looks like a minus x squared under a root. Y'all see that? So what would my trig sub be? R is equal to, what happens when you have a constant squared minus variable squared? A sine theta. A sine theta. So for us, I'm going to do r is equal to, r because our variables are, r is equal to 1 sine theta. What does all that square root stuff turn into? Square root of 1 minus r squared. What's that going to turn into? 1 cosine theta. So just cosine theta. What is the dr going to turn into? Cosine theta d theta, right? Go with me? All right. So now let's see how bad this gets. We're rewriting the integral now. Arafat, are you okay with what we've done so far? Okay, you ready to rewrite it? Okay, so what's that new integral going to turn into?
It's going to be 1 minus sine squared theta.
Where are you getting that? Oh, I've already done that. I've already turned this. I've already said this is going to turn into cosine theta.
So cosine theta
Uh-huh.
by r to the power sine theta.
So this root is cosine theta, right? What do I still have here, though? 5th. Okay, I didn't hear that. That's what you said. So to the 5th, and then?
And then sine theta, like sine to the power 8.
On the bottom, right? Okay.
And
That.
is cosine theta d theta.
Cosine theta d theta. That's it, right? That's it. Good? I mean, not good as in we're happy, but good as in that's what it becomes. Okay. So let's see, what is this going to be? This is going to be cosine to what power? 6th theta over sine to the 8th theta d theta. And that looks somewhat horrifying, doesn't it? No? This is integral, let's see, do we have cosine to the 6th theta over sine to the 6th theta times 1 over sine squared theta d theta? I'm just thinking through this. Like I said, I haven't worked this, so I'm just thinking cosine over sine is, well, cosine squared over sine squared, or just, what's cosine over sine?
Yeah, you can multiply it as sine squared.
I mean, it looks like you're setting it up to turn into cotangent.
Yeah, that's exactly what I'm going for here. Cotangent to the what? That's not a cotangent, that's cosine. Let me come back over here. So this looks like integral cotangent to what power? 6 theta. And then 1 over sine squared should be cosecant squared theta d theta. And what are you thinking about that? You should be happy to see that.
Because we have an identity for cosecant squared theta.
More than that, we have a basic u sub now. What's the derivative of tangent? Secant squared. What's the derivative of cotangent? Negative cosecant squared. So u is cotangent. Here's its derivative. We're off by a sign. So I'm going to make a basic u sub now. U is equal to cotangent x, or not x, cotangent theta. The derivative of that is negative cosecant squared theta. Do you all agree with me on this? Y'all are okay with that? Yes? And so we're off by a sign. So I'm going to say negative du equals cosecant squared theta d theta. And I'm ready to rewrite the integral. Can I keep going? David?
Yes, sir. So then you would rewrite it as u to the 6th power du.
And then we need the
Negative.
negative, right? So let's just throw that out there. And that yeah.
You got it.
That's awesome.
Negative 1/7 u to the 7th plus c, right? Yeah. So that's just power rule, right? Now we have to get from u all the way back to r, right? So this is really negative 1/7 cotangent to the 7th theta plus c. And now I need to know what cotangent of theta was. And way back somewhere, we made a substitution. We said r was equal to sine theta, right? And from that, I can do a triangle where this is theta, that means this is r, and that's 1, and that's square root of 1 minus r squared. So I can create my triangle off of my original substitution. And cotangent, by definition, is the adjacent over the opposite, right? Adjacent over opposite. So this is negative 1/7 times the adjacent. What's my adjacent? Square root of 1 minus r squared over my opposite, all of that to the 7th power. Plus c.
Isn't there supposed to be an inverse sign if we're solving for theta?
No, because there was never theta by itself. It was cotangent theta, and that was it. Like in the previous problems, we've had thetas appear, but that's because in the previous problems, we've used the power reducing formula, which gave us a 1 minus a trig function, or 1 plus a trig function, and then that 1 became a theta. Here, we never had that. I'm somewhat skeptical about this answer. What? Why? Yeah.
So I have a question about the very beginning. When you rewrote the 1 minus r squared over the square root, what's the rule for the property that makes you take out the 5?
I'm using this property right here. X raised to the fraction m over n is the nth root of x to the m, which is also the nth root of x all raised to the m. So these are all equivalent. So when we have something to the 5 halves, I rewrote it as, right, that's my m and that's my n. I'm using this formula right here. So I'm doing the square root of 1 minus r squared raised to the 5th. Is that what you're asking? Yep. So this is a property of exponents. Most of the time, students are shown that, but this from here to here maybe not as stressed as much. It doesn't matter what order you do it. You can do x to the m first, then take the nth root, or you can do the nth root of x and then raise it to the mth power. All right, so I said I was a little skeptical. I'm not real skeptical, but like I said, I haven't done this problem before, so I'm just going to check my answer real quick. Okay, so I'm going to take the derivative of this. So if I take derivative of this, I've got, well, who cares about the constant, but the 7's going to come out, right? And that's going to become what out front? So I'm taking derivative here. It's -1, and then all of that to what power?
The 6th.
All of this to the 6th power times, now chain rule, quotient rule, right? So I do quotient here. What's the derivative of the top? 1 over 2 square root of 1 minus r squared times the derivative of what's inside, -2r. So that's derivative of top times the bottom, which is r minus the derivative of the bottom, 1, times the top, square root of 1 minus r squared. I know I'm writing really small, but all over the bottom squared, so r squared. Okay, so this is negative square root of 1 minus r squared. Yeah, I'll just keep it like that. Over r to the 6th times negative r squared over the square root of 1 minus r squared. So I've already put all that together. And then minus square root of 1 minus r squared, and then all of that over r squared. I'm going to get a common denominator between these two. So I introduce a root on the bottom. And if I do that, then the top becomes that. Like I said, I'm only doing this because I want to check, okay? Now I get times, let's see, negative r squared. When I do this, minus 1 plus r squared. So the r squareds are gone. So I just get minus 1 on top. And then over my common denominator, square root of 1 minus r squared, but then all of that over r squared. So all of that becomes that. Okay? And then in front of that is this negative, right? So I'm going to get rid of the negative and make that a positive. And then I'm going to just go ahead and take that square root of 1 minus r squared to the 6th, put it over r to the 6th, and I can already see that those two together give me r to the 8th. And then this on top of that one of them cancels. So you get 5 of them. So you get square root of 1 minus r squared to the 5th, which is that. So it works. Yeah. Good. It better work. Next one. This one's tricky. So we are now stepping into some problems that are a little bit tricky in the sense that these are not going to be glaring out Trig Sub. It's not going to be sitting there with big flashing lights going, I'm Trig Sub, come, use a Trig Sub on me. It's not there. It's not obvious. So I guess what's the point of a problem like this?
Would it be reasonable to say you could put square root of 4 minus x over square root of x?
Sure, you could do that.
And then use up?
Well, if we did that, let me write it down, what you're suggesting, would be completely legal in terms of algebra, right? Doing that?
Yeah.
The problem, well, you tell me, what's the problem with that? Why is that not quite Trig Sub right now? Like, what do you have to use Trig Sub?
A square.
Square. Yeah, you have to have a square on that variable. Like, the Trig Sub needs you to have a squared minus x squared. And the reason you need it to be squared is because, remember, when you do your Trig Sub and you plug things in, you're going to wind up using a Pythagorean identity.